Welcome back, everybody, to our AI Summer 2024. This is our final day of the AI Summer. It seems incredible that it's come so quickly, but here we are. Today, we're going to be doing a couple of different things. First of all, I'm going to start out with a number of questions for you about architectures and seeing what we understand about transformer models. Then we're going to be taking a look at a really cool small model. We're going to see what's possible with even small models. Then we're going to see an example of what we talked about on Wednesday, this multimodal model that uses this trick of doing projection directly into an LLM, where the LLM is supporting all of the representations, a nice lightweight, easier to train version of a multimodal model. Then we're going to take a look at some uses of long context models. And that's what we're going to be ending with. We're actually going to be ending with a walkthrough that Abby's going to give us on something that she actually shared with you all last week, which is going to show you how she did it and how she used long context models to do it. And then I'm going to end with a conversation with a long context model about a very important paper that came out just about 2 weeks ago from Anthropic on monosemanticity, which you would think, how important could be something about monosemanticity? What is that anyway? Well, we're going to be talking about that. We're going to be taking a look at 2 pretty long papers, but conversing with them using long context models. Before we get started and before I start asking my questions, what questions do you have for me or for anybody on the data science team before we get started? All right, then I'll ask my questions. Let me remind you, this is a graph that we've seen lots and lots of times. Let me ask you this. Oh, I don't want to do the full slideshow. Let's go and redo this. Here we go. So here we're taking a look at something that we've seen quite a bit. This is just a visual representation of a transformer network. Couple of questions for you. First of all, we have multi-head attention here. Can somebody just describe to me what attention is doing?
Can I try answer that question?
Please do.
Is to take the average and looking at the token, in this case, some words to find the average point. So the example you always give us is to differentiate, is it the king, me, or the king that we're playing the chess?
Nice. So I love that because mathematically, that's actually what's happening, right? So you have this in right here is all of these embeddings, right? So these embeddings in this high dimensional space, these are long vectors, all the same length because it's the embedding space, that's the dimensionality. And what you're doing is you are preferentially blending, averaging those long vectors to re-represent a particular token's embedding with respect to all the other tokens that you have in the sequence. Exactly. So if I say king me, that's a verb, and that means I'm playing checkers, versus the king on the throne, which is a noun, which is something like a regent. Absolutely. So another way to sort of characterize this is that with multi-head attention, or with attention, those tokens are informing and communicating with each other. So this is information across all of the context. So as long as your context is each one of those tokens gets to be informed by all of the other tokens. Let's compare this to our own working memory. Does anybody know how long our own working memory is, where we get to keep the number of things that we could keep in mind all at once? So in our own attention, biologically defined, how big is our attention? So multi-head attention like this could be 8,000 tokens. This longer attention looks like 32,000. You remember we have Claude, which has 200,000 tokens, and we have Gemini 1.5, which is 1 million or 2 million tokens. So really, getting big. How big is human attention? I see that we have, yeah, so Zingbo, small, yep, absolutely. Sophia, yeah, 7 plus or minus 2. George Miller's paper from, gosh, when was that, 50s, 60s? So our attention actually turns out to be much smaller. So when we do that kind of blending work, when we have things completely in mind, we're talking about far, far less. So the way that we do that blending has to do with a combination of longer term stores, right? And what we do is we store it and then we do extra processing. And so it's really effortful for us to be able to do that. So that's sometimes one thing that's a little bit difficult to understand about these models is their attention mechanism, of course, is completely different from ours. And also there's this idea that however long your context is how long you can directly compare and combine information across multiple different, all the information that you're holding all at once. Fantastic. This is great. Feed-forward networks. Can somebody tell me what feed-forward networks are doing in this setting? So we've just said attention is allowing each of those token embeddings to inform one another. What is feed-forward doing?
I want to try.
You're going to try again?
Mm-hmm.
All right, so
So
fantastic.
each stack has its own feed-forward network. If I say multiple stack neuron decide how many stack and neuron we want to get to the result we want. So basically, more stack equals to more reasoning and more runtime. How did I do?
Well, I mean, you're absolutely right. The more stacks that you have, the more kinds of processing you're going to be able to do. Absolutely. We're going to actually see an example where even if you have limited stacks, you might be able to get really good performance. But yes, longer stacks are the more stacks, the more processing you can do. Let's think about this in relation to the multi-head attention, where with attention, you have tokens communicating with each other. The embeddings inform one another. So now think about what happens with each embedding as it goes through a feed-forward network. Does anybody, I characterized this once. So with feed forward, what happens to each of those embeddings? And remember, we have the agreement where if I call on you, you can pass, right? But I think some of you have some ideas, but if you want to pass, you can. No harm, no foul. Ezra, would you mind? What's your thinking about this?
So going back to that 3 blue, 1 brown video about propagation,
Yeah.
it was discussing how within the neural network, like the connections between what essentially I think are the embeddings of the tokens are if they're wired, the way I'm thinking about it is essentially it's grouping tokens that are associated together on like semantically connected together.
Okay, so we're hitting on something, right? So if you think about that embedding as going through almost like a pulse, that's like the impulse, right? That's one message, it's one signal, it's going through, and then something happens as it's going through around the semantics. So one token is being modified by the semantics. So it's the enriching of each individual embedding. As each embedding goes through, it gets enriched. So if we say the king on the throne, now Before, it might have been a little bit impoverished, where it's just like, okay, something like region, but now it gets enriched with all the knowledge of the feed-forward network to fully inform what it's meant by king on the throne. So king on the throne means not dead, right? It means, a male, who, and this is a monarchy, and this is, you might even have the idea of like, if the king is on the throne, you might be thinking of like a crown, so I mean, all of those things are enriched into that one embedding of king. So attention communicates across tokens. Feed forward enriches each individual token, not any communication between the tokens, but each token gets enriched now with additional information. Great.
So there
go ahead.
isn't that there aren't the connections between the tokens during this phase?
Well, not between. So in that visualization that you have in your mind, what's really going on is that each node has associated with it the weights and the activations. So really think of the embedding as being the signal that goes in. What information are we giving? The token is just the activation which goes in, and then the enriched token is the activation that comes out. So let's say a vector of 768 goes in and a vector of 768 comes out, but it's been modified. But unlike attention, where each of the vectors informs one another, you might have a whole bunch of vectors that's 768 long. Let's say you have 2,000 tokens in your context. So each of those 2,000 embeddings, vectors, are being sort of averaged together. Now what happens is, one by one, you're taking one vector and you're modifying it, enriching it with additional information. So the embeddings are just activations. Now, this is a key point. The really interesting stuff that's going on in these networks, in these transformers, is activations. So embeddings are activations that are moving through. It's the values that are going on. So if we want to explore what's really happening when you're processing, when you're doing something with these networks, you can't just look at the weights. That's kind of a mistake that people made for a while of, well, if we understand the weights, we understand the network. But in actuality, it is the activations and what happens with the activations over time as things move through. So that's going to be important, especially for the end of today, to keep in mind. If we want to understand what's happening with the networks, we've got to understand all of those activations as they move through. Great. All right. Another question then. Okay, let's see. Oh, and there's something in TAP. Data move through the network to produce an output for embedding. The weights are learned during the training each. That's right. So the weights are learned only during backpropagation. That's when the weights are learned. That's the visualization that you saw before. So that backpropagation is only during training, and it's when we're doing this, the forward, when we're doing the inferencing, when we're actually using the models, that's where none of the weights change, but the activations are changing all the time. Fantastic. All right. What is the most expensive thing to do here? So all of these are computations, but what is the most expensive part of this in terms of storage that you have to make while you're doing the calculations, and just the amount of compute you need to do?
During training, or?
No, actually during inferencing. Well, actually, it would be during training too. Yeah, you're right. But I'm thinking even just during inferencing, just to get this thing to run. But actually, it's going to be both. It would be both. What'd be the most expensive thing to do here?
Probably the multi-head attention, because you have to multiply big matrices.
That's it exactly. Multi-head attention is extremely expensive to do, and in the purest form, the simplest form, you're doing because you're doing pairwise communication, right, between all of the tokens. You're going to have to do n squared for just a single pass, n squared. So that is a ton of computation. And remember, I mentioned it is all the tokens in the context have to be able to communicate with one another. That's what attention does. So one way to handle this is early models had very short attention. Why? Because it was so expensive to do. So that just meant you had, the very first ones, you had like 512 tokens. That was it. 512 tokens, and then you ran out of time, ran out of space. You couldn't communicate with the model anymore. You would forget what it had before. Just, that was kind of the limit. Then we were able to get bigger by doing more and more efficient attention. More and more efficient attention got us up to like 8,000 tokens. That's kind of useful, but then up to 32,000 tokens. Then now you have enough room to do an ongoing conversation where everything is remembered, where you can have more information that's in there. And remember that communication between all the different tokens, this is very useful to be able to do. And through even further, more efficient ways of representing attention, you can get very long, 200,000 tokens, million tokens, 2 million tokens. One way to do this is you do actually not allow all tokens to communicate to all other tokens. That's one thing you can do, but then you lose the real power of attention. So know that a lot of attention has been placed in the last couple of months, especially. I would say about 4 months ago, there was a lot of work around how to increase the attention length, the context length of models. And we're going to see at the end of today what some of how this got to be useful. And I'm not going to go into the specifics of how this is done, but know that it's important to still denote in some way where each token is. That turned out to be a big problem to solve, and also to figure out how to do this type of computation in a very efficient manner. But in many ways, that's been addressed pretty well. Certainly more advancements coming. But right now, you can reasonably get up to 200,000, a million tokens, and perhaps more, and yet still have some communication between all the different tokens. That means long context, long conversations, a lot of material that you can all interact with at exactly the same time. So questions about this?
Jesse, I have a couple of questions regarding what you just said.
Yeah.
One, it seems again kind of astounded that this wasn't discovered earlier, because it seems just a math trick, or so, like effectively
The whole idea of attention.
Yeah, the whole idea of attention. And so was it more that, it sounds like even just 5-7 years ago, there was no computation. The computation wasn't there to do much more than maybe 10 or 20 by 20 matrices. But then second to what you just said is, it seems like that if you get too big, my intuition would say in context, you're almost putting in too much junk in the context. And so like, do you lose something if you have a million tokens where a lot of it may be irrelevant, even if you can do the computations now?
Yeah. So to go back first to your historical question, the idea of averaging in these embedding spaces had been around for a while, and even the idea of having an attention mechanism was around even as early as, well, I'm trying to think, there was attention in RNNs as early as like 2013, 2014. I think there were some papers on attention, but what they were doing is they were only doing attention once at the end. So let's do all this work and then let's do it. So it was only at one point, maybe at the end, maybe earlier. But the real breakthrough here was this idea of marrying attention with a feed-forward network and then doing that in stacks. So this idea of, okay, let's have communication between tokens, and then let's enrich each one, and then let's do that in stages. It turns out that was the secret. That's what's really important, is you allow for iterative improvement and enrichment. That turned out to be really important.
Okay.
Go ahead.
No, that's great. That's great to know. Thank you.
Mm-hmm. And part of the problem was that RNNs, recurrent neural nets, were really tough to parallelize. So they were really hard to compute and to train. It turns out that you can do better parallelization if you actually do this stack. You can actually run more in parallel. And then there was a second thing that you mentioned that I have lost track of.
The infinite tokens, or the $1 million, though you lose some edge by just
Oh, right.
shoving a lot of stuff in there in the
If you're
context.
shoving indiscriminately, then yes. However, if you curate what's going into that, and depending on what your task is, if you have a bunch of irrelevant information, then absolutely that will tend to wash out what is not, what is relevant. But remember that this is dynamic, right? And so if you begin to so imagine you have this wide-ranging conversation, right? And it's just going all over the place. But then you say, you bring something up that was discussed earlier. Now remember these activations, each time you put in a new token, it reruns everything through, and so it gets to recalculate what the weightings are. So it's not as if things are static. So if you bring something up that recall something earlier in that conversation, now, as you run that through again, auto-regressively, you put that new token in, you rerun everything. Now that's going to change what the activations are, and the relevant parts get raised up. So it's not that it's just all noise, because they don't all have equal, activations. That's changed dynamically each time you add something. So one way of sort of testing these out is needle in a haystack. Can it actually find the things, even though it's buried in irrelevant things? It turns out, yeah, it can do a pretty good job if you are careful in how you're extending your attention. And it's up to you to put relevant things into the context window. That's why you need, for RAG to work, it's got to work, pull out the right things. For long context, you want to put the things that are relevant for the things that you're going to be doing. Sim.
Hi, I think I confused myself when you talk about money, the cost. So we want to have more attention so I can get all this result in. But in my way, I was thinking about the place that I would spend more money will be in the decoder stack, because on the feed-forward network, I want to make sure that I have more reasoning, means I need more stack, I need more runtime. Isn't that I will spend more money over on my decoder stack instead of the attention, because I want to get the result I wanted?
Yeah, well, let's go ahead and just be specific. It really helps to have your feed forward network big, because that's your knowledge. That's your world knowledge, right? So if your network doesn't know anything about kings, you never trained on it, was never, never learned it, then it's not going to be able to do any enriching on that token, right? So you want to have your feed forward. This is often where the networks get big. They get really big in the feed forward network, but all things considered, they're pretty cheap to compute. It's a straightforward matrix multiply. So you don't have to spend compute on that, meaning matrix multiplies are cheap. We can do them quickly. We know how to make them efficient. They're easy to, algorithmically, they're straightforward. Attention is n squared computation. As that context length gets long, it requires more and more compute. There are things that you can do to make it efficient, but you have to pay attention and make that efficient.
Gotcha. Thank you.
And that's really what's meant.
Mhm.
Great. All right. Let me ask you all this then. How do you make models better? Tell me some ways that, and actually, Sim, you just brought up one, which is, one way is make your feed forward networks bigger, right? So they have more world knowledge. What are some other ways to make your models better?
Fine tuning.
Okay, absolutely. So you can do additional tuning of the models, and so they might learn a new task. They might learn more information. So additional training. And let's go and say that additional training of the models can make them more knowledgeable or better at a particular task. Fantastic. What else can you do?
Back propagation.
Right. That's how all that training is going to happen, right? So backpropagation is the process by which this happens. Great. So more training, that's good. What are some other things? So what are some decisions you can make if you're making your own network? What are some decisions you could make to make the model better? Awesome.
More training data.
Ooh, okay, great. So one of the things that you're finding is that people are doing are instead of using, it wasn't that long ago when it's like 1 trillion tokens, we trained on 1 trillion tokens. Well, some of these models now are trained on 10 trillion tokens. Absolutely. Is that any data? Is any data good? Just more is better?
I mean, more could be problematic too if it's toxic stuff, I guess.
Okay. Toxic. Yeah. Garbage. Garbage is bad too.
Mm-hmm.
So maybe more data, absolutely, but even better data.
Yeah,
Okay,
higher
Maxwell,
quality.
right? Training with pre-filter or higher quality data. Exactly. So it turns out that the quality of the data that you're training on is also extremely important. Matter of fact, with the Gemma models, one of the things that they did was in the later Gemma models, they got much better performance by training on the garbage data first. Garbage data, I mean, like unfiltered or stuff that, where there are lots of misspellings, maybe grammatical errors, maybe formatting code, things like that. But that's where you trained on early, and that's where the model just first began to figure out, oh, there's this thing called language. Oh, there's this thing called English. And so the very rough, and then later trained on the very good material later to get the facts right, to get the information right. So absolutely. So the quality of the data that you train on is extremely important. The other thing that happened, I don't remember if this was called out specifically in Gemma or if it was called out in Llama, that one of these models trained on Python code earlier and more of it. In addition to being better at programming, can anyone guess what else it got better at besides programming?
Instructions?
Instructions and reasoning. That's right. So the model, because it was trained earlier on the code, represented the later learning more in terms of problem solving and logic. And so overall, the model became better at reasoning. So just by choosing what we train on, when we train on it, how much we train on it, we can actually get very different types of performance out of the model, which of course, if you think of it, makes sense. It's like, if you train the model on Mandarin, it's going to learn Chinese, duh, right? But depending on the quality and when and the order in which you train will also influence how the model works and how it responds. So what we're going to do first is Miranda's going to talk to you a little bit about a model that's able to achieve much more than you might think. And part of the real secret sauce here is not different in terms of the architecture, but the real secret sauce here is the training. Miranda, can you share a little bit about the model?
Yes, so I will go ahead and share my screen. So we're going to be working out of one of the notebooks on the AI Summer repo here. So if you go to our AI Summer repo, it is 4.2 Phi Vision example. So you can click on that. And hopefully the opening, yep, there it is. Open and collab should pop right up. So I'm going to be working with this. And this is just a quick notebook that we wrote up so that you can know how to inference with a model called Phi. So maybe you recall on Wednesday, we talked about multimodal models. We talked about models that can take input or output text, video, audio, images, really a multimodal model. And sometimes these are hard to run, but the Phi is one example of a very lightweight model that is very easy to run. So really excited to be able to show this to you today. And most of this code, I did customize it a little bit, but most of it I actually got from their Hugging Face space. So if there's a model you're interested in and it's on Hugging Face, definitely check out, they call this the model card. It's going to have a summary of this model as well as, some inferencing here, and also how you can use it. So there's a whole suite of Microsoft models on there, including Phi, a whole suite of Phi models. And you can kind of get a little sense of it here. So it says Phi 3 Vision 128K instruct. So what you can get from this here is, Phi 3, it's their latest Phi model. It's a vision model, so it can look at images, and instruct, so it can take your, it's that instruction fine-tuned type of model, so you can give it instructions. And multimodal model built upon data sets which include, and this is what data, this is the data that Jesse was talking about, synthetic data and filtered publicly available websites with high quality, reasoning dense data on text and vision. So very, very nice training data. And you can read about it as much as you would like, but if you keep scrolling down, it tells you the packages that you need. This is very important. So where you will see the pip installs on the Google Colab, go ahead and run those, and then I'll talk about it. Or it'll run while I'm talking. So go ahead, and I already put these on here for you, but you can see what packages you need. It even tells you, how it was trained, what the chat format was. And then this is really the best part, where it gives you an example of how to use the code, how to code with this model. So you can go ahead and select it using the transformers library. You can set up your model, your processor, just based on that model ID that you give it. So it's very easy to set up. You just need to have the name of the model you want to work with. They've provided an example image, and then some arguments here. And so basically I just took this and kind of, cause first I will have this exact example and then show you how we can change it around a bit. All right, so let's go back to that notebook. So I have already run this. If you haven't already, go ahead and run this, and do pay attention to this part. Be sure you are connected to either the A100 or L4 GPU on Colab. So if you go here and change runtime type, either the A100 or L4 is what you want here. That is because of, which library is it? I believe it's Flash Attention, which is a type of a new type of attention, new-ish, that requires those specific GPUs for some reason. So on Colab, make sure that you are connected to either the A100 or L4. And I already ran this as well. It doesn't take too long to run, but this is just getting our libraries in and then starting up our model. So we've got our model ID here and then setting up the model. So this is just from Transformers Auto Model for Causal LM. We're basically setting up our chain here, setting up our processor as well. And everything looks like it downloads okay. So this is the image that is in their example on the Hugging Face space. And one thing that I want to point out is that this is a chart. There's not if you don't know how to read charts, if you're a model that doesn't know how to read charts, it'll be very difficult to process. You'll maybe say, oh, there's some squares. And a lot of the early multimodal models were not good. I think still, if you go to ChatGPT 3.5, maybe, uploading an image like this, it's not really going to be able to tell you a lot about this chart and what it means. Maybe it's not 3.5, maybe it's 3. But for a while there, we couldn't get a lot of multimodal models that not only understood images, but then were able to extract kind of the text from them and understand what different charts means and stuff, which I think is probably one of the most requested use cases that we get for these multimodal models, is reading in charts, reading in graphics that humans can process, but computers have a little bit of trouble. So I thought this was an interesting example that they gave us here. Now here we're going to set up the messages, and this is kind of a way to preserve your history of messages if you want to include more than one. So this is just set up just the way they have it on Hugging Face. Notice this placeholder here for an image, and it says what is shown in this image. This is the URL of the example image. And what we're going to do is put that prompt through our model and generate these IDs. And I'm trying to remember if I already ran this one. Let's go ahead and run it. It doesn't take too long. But what this is going to do is go through and then print that response for us from the model. There we go. So see, it doesn't take too long. It says this image displays a bar chart showing the percentage of respondents who agree with various statements about their preparedness for meetings. The chart has 5 vertical bars, each representing a different statement, with percentages ranging from 75% to 79%. The statements are about having clear and predefined goals for meetings, knowing where to find information for meeting, understanding one's exact role and responsibilities when invited, having tools to manage admin tasks like note-taking or summarization, and having more focus time to sufficiently prepare for meetings. Oh, it keeps going. The source of the data is Microsoft Work Lab. This is super cool. It's able to read this chart. So let's go back here And, you know, I'd say it was pretty spot on. So we've got a range of 75% to 79%, percentage of respondents who agree. Says it, notice it doesn't really say that it's about meetings, but it was able to infer that from these descriptions here. So having clear and predefined goals for meetings, tools to manage admin tasks, understanding my exact role and responsibilities when I'm invited. So pretty impressive, honestly, that it's able to read this chart. I was really excited to see this, but I also thought, you know, maybe Microsoft is giving us, because this is from Microsoft Work Lab, maybe it's giving us something that they know it will do good on. We don't know if the model was actually trained on this image or not, or you know, that Microsoft, it's important to note that the source is Microsoft, and Microsoft gives this image to work with the Microsoft model. So always keep that in mind when you're doing these little examples. So I thought, okay, I'm going to give it something that it definitely has never seen before. My cat. Keeping with our theme of cats throughout AI Summer. So actually, you can upload whatever image you would like. I do provide the URL. I put an image of my cat on our GitHub. So if you would like to work with him, he is beautiful. But how I put this on Colab specifically was if you open this little folder thing, you can upload a file. And let me find my picture of my cat again. Okay, and it's just going to give you a little warning that says that, you know, this is going to disappear after you exit this Colab instance. So now I've done this. I'm actually going to rename this file my image just because that's how I refer to it in my code. So I can open this just by using, you know, accessing it just as if you were on a computer. This is kind of your working space within Google Colab. So a pretty neat way to be able to access files. And so here's my beautiful little cat. His name is SoundCloud. And if you would like to use this exact picture, if you don't have a picture that you want to upload to Google, you can uncomment these lines, just erase this little these little hashtags here, and you'll be able to use that image as well. But so I thought, okay, I'm going to upload this image and see how this model does. So I've kept everything the same, except, no, I think I have kept everything the same. So if you recall, our prompt is still insert image. What is in this image? Please describe it. And I'm going to redo this so that you can see it, although the output is saved there. And it says this image shows a Siamese cat lying on its back on a carpeted floor with his paws up in the air and his head tilted upwards, looking upwards. I think that's a great description. I'm actually, some of the things I was impressed with, I was impressed and knew it was a Siamese cat. The fact that it got this texture here and that he's lying, you know, on his back with his paws up, I thought it was pretty pretty neat what it was able to pick up here. And, you know, perhaps you could even ask more questions about this. So in fact, I thought, you know, maybe we'll try something a bit more fun. So now I'm going to keep this in the so this is, like I said, it's a list of the messages that we've had. And so it looks at this message. And then it's going to look at this message and say, so I'm going to say, write an Instagram post to go with this picture. Maybe I want an automated Instagram account for my cat and we can go viral and I will be rich from my cat. And so let's write an Instagram post to go with this picture. I did the exact same thing. Notice that I haven't changed anything. I've just changed the messages that I'm sending through with my prompt. And it comes up with this one. I'm going to run it again just to show you. Oh, I didn't run this. Make sure that you run your new message. All right, so now it should be generating that Instagram post. And what's fun to note about this is that you can really, you know, make this whatever you would like. You could say Reddit post, you could, you know, ask it a different question entirely. You know, propose names for this cat or something. And it's taking a little bit more time. There we go. Okay, so cat emoji, perfect for Instagram. This little feline friend is taking a well-deserved nap under a cozy blanket. Their soft paws and adorable blue eyes make this moment even more precious. And then I love these hashtags. So heart emoji and then hashtag for Instagram, cat lover, pet lovers, cute pets, furry friend. It kind of goes a little crazy on the hashtag, one thing that I want to point out that made me cackle is if you keep scrolling here, so it's really crazy about these hashtags: pet lovers club, cat photography. This is where it starts going downhill. Cat photography tips, cat photography tips and tricks, cat photography tips and tricks and tips, cat photography tips and tricks and tips and tricks, cat photography tips and tricks and tips and tricks and it keeps going. And so this is the best one here, the best hashtag. Maybe you'll get a lot of views on Instagram for this, but tips and tricks and tips and tricks. This made me laugh. And so sometimes the models, you know, are not too great, but notice here that I did have the temperature down to 0. And this is an example of where you can kind of get stuck with your model. And an Instagram post is something where you would want it to maybe be more creative. You want your Instagram post to stick out, not exactly in this way, but you want your Instagram post to maybe be a little more creative. So we can actually tune this temperature here. This is kind of, you can think of it as the creativity or the reproducibility of your model. So actually, and then the next one, I thought, okay, I'm going to ask for something different. So I changed this temperature here. Notice I also changed this do sample to true. Bad programmer, I did not actually look into what exactly this does on their API. It was just that I got a warning that said I couldn't set temperature and also have do sample equals false. So pay attention to those little warnings. Sometimes they are helpful. And next time I will do my homework on what exactly this flag means here. But I set the temperature up to 0.8, hopefully, resulting in a more creative post. And in fact, it did. Now it says, cozy corner of my life, little Siamese kitty named Whiskers. It named it for me. Just discovered that despite their names, Siamese cats, blah, blah, blah. And so, it's got a little interesting post and then says, what's the most surprising thing you've learned about a pet today? And then a little bit less hashtags here. So that's pretty good. And I thought that was a pretty cute post. And you could even, give it a better prompt to say, I want my post to be about XYZ or something. So just a short little demo of the types of things that you can do with Phi. I thought it was pretty impressive and fun to mess around with. So I would love to see what you all are able to do with this, and definitely share if you got some interesting results. But that's what I have for you today.
And how many parameters is that? So keep in mind that the other models that we're dealing with are pretty much are pretty decently sized. So do you remember how big Phi3 is?
This is the 128K.
20 for the context length, right? Yeah. And for the parameter count, do you remember?
Oh, for the context length. Oh, yes. For the parameters, let's say, where does it have this? It's not a lot.
This might be the 7 billion
interesting.
parameter one. Is that?
I think it might be. I thought it would say on their card.
I really should.
3.8
oh, wait a minute.
billion
So yeah, so this could be mini or it could be small, but actually, yeah. So really far fewer parameters. So you might, for the performance that you're getting.
4.2 billion parameters for Phi3 vision. That's pretty crazy.
4.2. Yeah, that's just insane. And so not only is it a decent LLM, it's a VLLM, so it can do vision. And so this really is a great example of the importance of very good training sets and being careful with the curation of your training sets. Thank you very much for sharing that, Miranda. Let's go ahead and let me mention one more time these VLLMs, and remember that we're doing projection of that image directly into an LLM. Abby, would you want to share a little bit about Lava?
Yeah, I can talk a little bit about showing what Lava is able to do. I will share a screen. Okay, so we had talked a good little bit about Lava yesterday, or last time, which is a pretty new and really pretty powerful model that is able to interact with images pretty well for especially given that it's not gigantic, it's much bigger than Phi, but it is not massive. So it's reasonable to like fine tune it. And it's pretty incredibly performant at some tasks, although I will show a task that I found that it's bad at, which I always just think is funny when models are really bad at certain tasks. I'll put this, so this is their official demo page, which if I can find the chat, I will drop into the chat. So this is maintained by the people who made Lava. They also linked to this on their GitHub, and I believe that this takes you directly to kind of the resources that they've put together really nicely that show off the demo, kind of cover all of the different versions that they've made. So they've made lots of sort of updates to Lava, lots of papers to read, but they also do a pretty good job of sort of explaining those here within their Lava website, going over, you know, everything you need to know. But they've also put together this great demo page that just kind of you can play around with, so you're able to interact with that inferencing task kind of without needing to write any code. So I have a few examples. The first thing that I'll show is this, which is, as Miranda was saying, I think the reading of, did that not upload? Oh, I hit cancel. The reading of diagrams, I think, is always kind of a, you know, a task that comes up a lot for these models to be able to do. It's incredibly useful for like so many workflows, and Lava is able to do this pretty well. Sorry, I'm trying to just move my window. Okay, so I have here a diagram that I had drawn up for a class that I took earlier in the semester, the NSF's National I-Corps program. And as a part of this program, we had to draw up, so this is a hand-drawn, an example of what we think a customer ecosystem diagram might be. So this is a very personalized thing that I drew up by hand for the particular project that I was working on and going through this program for. So I know that it's never seen this before, and it's also handwritten, and it's very messy, and it was done in like 5 minutes in the class as like a little brainstorming activity. So I'm going to ask it questions about this and see what it's able to tell me. So maybe I'll start by saying like, this image was drawn for a class. What class might ask for an image like this to be drawn, and what is the image of? I don't think that I put a title on this image, and here we can look at it. So this is the image in question that it's going to work on for a sec. So you could see that we have, you know, these different color-coded arrows that I've drawn, and information kind of flowing in and out of all of these different pretty like messy areas going on here. So I've just asked it to read this for me and tell me what this would be about. The first thing that I think is always super cool is that it's just able to directly read text, even if it's handwritten, and my quick handwriting on an iPad is like not fantastic. It's able to understand all of the different kind of things that we have going on here. And they're not necessarily obvious. So this was kind of a particular product we were working on where stuff like parents and children are involved, but so is like lobbyists. And so it's not making up that all of these things go together, right? They are directly read from the diagram. It's you know, able to figure out that, shows how the entities interact, complex networks of influence and resource flow. Thinks it's a class maybe on education policy, public administration. Okay, so it's hard to figure out exactly what the class is, but I can ask it, this was the customer ecosystem for a product. What product might have a customer ecosystem like this? Okay, so the first thing that it comes up with is that this might be a piece of educational technology, which is exactly what this was. This was an ed tech tool that we were going through the I-Corps program for, which obviously has a lot of potential stakeholders, which it's able to identify. And so, yeah, this is just a great example of kind of a handwritten little diagram, and the question answering that I'm able to do about it is like, it can pick out this kind of complex ecosystem and figure out kind of roughly where actually the piece of technology that I'm targeting like was within the ecosystem, just kind of by looking at this not super well drawn diagram. So it's a very cool use. Again, you can just go right to this demo and play around with it and do all this right on this website. I won't show this example. This was another example that I had, which was just loading this in and asking. I'll do it really quickly. And you can load in a new image, so I'm going to load in this one, and I'm going to ask it, like, I want to go somewhere like this. Where is this picture likely taken? So now we're starting a new chat about this picture. It's going to tell me it's a alpine meadow. Suggest a couple locations that look like it. It obviously cannot tell specifically, which is fine, but it does suggest a couple places that I could go. I had tried interacting with this image before and asking it to identify specific wildflowers for me. Which it does a decent job, given that I think the task of specifically IDing wildflowers is incredibly difficult. So it suggests a few types that are common based on the color. The lupines, for example, I think are some of this image is hard to look at. Are some of these, I believe, that kind of like stick up like that, for these back here, but it is mostly, I think, just going off vague color, because like IDing wildflowers specifically, I think is tough. I think a lot of wildflowers look kind of the same, and this isn't the highest resolution photo. But again, it was a pretty cool example. I think that in an earlier chat with this particular image, I asked it to kind of hammer down on some of the flowers, and we think we identified one as being in like the Western United States. And I said, okay, if that's true, like where might I find this in the Western United States? And it can suggest a location to go to where you're likely to find an alpine meadow in the Western United States based off of a wildflower it thinks it saw. So you can ask about these really specific things about these images, and kind of it understands when you're asking, you know, like I can say, what might the red wildflowers in the photo be? And it'll try to pick out characteristics about specifically the red in the picture, and try to identify based on some of the characteristics that they have. So yeah. And thank you for the tip about wildflowers. Yeah, I was trying to get, so yeah, I'm not a nature expert. I was trying to get it to be able to like be agnostic to location and season and see if it could still identify it, because I actually have no idea when or where this photo is from. I think that is a very difficult task, though. I think that's an unreasonably difficult task. And then this is the final photo that I have, to just show that sometimes, you know, things are never perfect. So this is a picture of a baby goat in a wheelchair, and it says that this is a dog. And it does get that it's a harness attached to a wheelchair. In a really funny version of this before, it said that it was on stilts, which is funny because dogs don't use stilts, which I just think is a funny. I think that it was trained, like I think a lot of the captions that it was trained on were sort of doing that higher level of like reasoning of what is interesting about the photo or what is, you know, that type of task. And so I have kind of found that just in playing around with it, that it will like try to give you that extra like, and this is what's weird about the photo. Even if like it's wrong about what is weird and it's not even weird, it like likes to throw that in. But anyway, so I mean, never perfect, but very funny. I love when it misidentifies animals. Okay, so that's just a great little demo of Lava. I just want to point out, so a few extra kind of resources for it. Yeah, their main page about it has tons of information, as does their GitHub, and there's multiple papers to look at. But it is also supported on Hugging Face. So there's in the Hugging Face documentation, there's documentation for Lava and Lava Next, which is the improved version of Lava. It even covers how Lava Next is better than Lava, talking about the higher image resolution and the way that it was trained. And because this is kind of built into Hugging Face, it means that doing inferencing with Lava through Hugging Face is very simple. This notebook is not on the GitHub yet, but I will put it on the GitHub for your reference. But it's really simple because they have these pre-built, you know, Lava for conditional generation, which is through the Hugging Face transformers package, that we can go to one of the Lava Hugging Face models and just directly, super easily load it in through Hugging Face. So in this example, I'm not going to run this code because I'd have to change my runtime and wait for Lava to re-download, and it's pretty big, so it takes a while. But we can just load in from the Hugging Face page, Lava version 1.6, super quickly. I had this image, which I believe was just of another alpine meadow. Can you tell that I love alpine meadows? And I asked just what is the content of the image, and just really quickly by just running through the model.generate, you can get that the image features a beautiful mountain trail surrounded by a field of purple flowers. So incredibly easy to also do all of that inferencing steps through Hugging Face because it's all available here. And there's many versions of Lava that are available. So if you just do Lava HF, we can see that there's a lot of different like versions of Lava. This was version 1.6, but they also have versions 1.5 available, which is a bit smaller. So all of that super easy to access. And you can also do, because it's all set up really easily through Hugging Face, that also means that it's super easy to train or fine tune Lava via Hugging Face, which I love when that is the case, because training through Hugging Face is incredibly simple. And so we saw this weights and biases code previously on how to fine tune Lava on a custom data set, but we can also use the built-in Hugging Face, set up a trainer and train, which I did not, that's why this notebook is not on the GitHub yet, because I didn't go through those steps yet, because you need quite a lot of GPU in order to do this. But I will finish that up and put it on the GitHub so that it's all for your reference, but super easy to fine tune through Hugging Face because that's all set up. So Lava is really great, easy to interact with, and still pretty small, but also incredibly powerful.
Thank you, Abby. So between the phi model and the Lava model, the important thing to keep in mind is that you can improve the models, the performance of the model, by choosing what backend, what LLM you're going to be projecting onto. So imagine that you actually want to train on an entirely new type of set of images. These could be medical images. These could be the wildflowers that we were just talking about. These could be pretty much any sort of a visual task you can think of. You could train the model on text around those things, and so train it quite extensively on the taxonomy and descriptions and all the information about wildflowers. Now, when you do a projection of pictures of wildflower onto this LLM, you're already going to get a better representation just because you have a better, more enriched LLM on which you're doing this projection. And that's true for any sort of the tasks that you want. You can also do additional training on that by again coming up with these image and then description, image task between the two as well. But it's really the first time that we've had within our reach the ability to come up with very specific solutions. And the fact that you can do this with approachable compute, with reasonable compute. The earliest Lava 1.5 you could train on a single NVIDIA A100. The later larger one does require more compute, an entire DGX, but still, this is, it was only just a few months ago when it would have required a server farm, and it would have cost you several $100,000 to train this. Now you're talking about anything from the smaller models for maybe 10, 20, 30 to a couple of hundred to maybe a couple of thousand, and then you have like your own personal trained model. And these models are the worst that they're ever going to be. This is them at their worst. Everything from this point forward is going to be better and better trained. All right, so let's go ahead and take a short break here, because next we're going to be talking about long context models. And I'm going to ask you a question when we come back. We're going to take 5 minutes. We're going to ask you a question when we come back. And the question is this: what are some things that you can do with long context models that you can't do with shorter context models? So I'm just going to sort of randomly ask some folks. I'll ask for people to volunteer as well. What are some things that are possible with long context models that are not possible with short context models? And we're going to start out, Abby, we'll start out with you, if that's all right, so you can actually walk through how you were able to come up with, a really nice demonstration that you showed last week using long context models. All right, see you all at, we're going to start up at 10:08, at 8 minutes past the hour. All right, 5 minutes. See you. Welcome back, folks. All right. So I ask you to think about the question, what can you do with long context models that you're not able to do with shorter context models? First off, do we have any volunteers? And then I'll just call on a few folks to see what your ideas are.
I will go. I will go.
Great.
You don't have to chop things down, so it can do a long context, and the short model cannot do that.
Okay. So you don't you can put entire, let's say you're doing, yeah, so you can put entire things rather than, so for RAG, for example, rather than just grabbing parts, maybe you'll put,
Chunking.
grab the entirety thing. Okay, got it. All right. Other ideas? Multilingual. Yep. So now you can do multilingual if you are even with short context, but this allows you to translate longer passages. Absolutely. Thank you, Zengbo. Let me call on a few folks and see what ideas that you have. And if you want to pass, you can, absolutely. Sean, do you have some thoughts on some things that you can do with long context that you can't do with short? And Sean, you might not be ready, so I'll call on someone else. Sean, okay, enhanced retrieval of info. Interesting, right? So if you put a lot of information into the context, then that may be a really good way to sort of find information that sort of might be buried, especially if you give a conceptual description of what it is, it's a way of sort of interacting with data in that way. That's interesting. I like that. All right. Let's see, Swapnita, what are some ideas that you have?
So I can speak based on my experience. And so one example is I was trying to develop a meal plan for pre-diabetic people. And recently there are a lot of examples going around for how AIs are just making up stuff, like you can put like a glue on pizza, or you can eat a stone to like
They're very filling.
your kidneys. So instead of it making up stuff, if I gave it like super long reasoning, it was giving better suggestions for a specific type of diet a person should follow. So use of long context to stop LLM from making up stuff or stay within a reason.
Excellent. So that the idea of giving it more context. Remember, with more context and with better context, the model is always producing that next token with respect to the context that it had before. So, you might say, every recipe you have ought to be edible and safe and great. Okay, excellent. So Emily, oh yes, and you have such an interesting project that we're going to be working on, curriculum materials drawn on a deep well of knowledge. So the ability to feed in all that information all at once is very powerful, especially when we think about the fact that with attention, every piece of information that you have is going to be interacting with every other piece of information. Exactly. So if you might even have a whole, a long paper or short book on a particular topic. And if you mention something, it will be able to directly access everything which is relevant to what you're putting in. So absolutely, Emily, I love that. I love that. Well, let me ask you about this. When you give an image, right? You give an image to a VLLM, how is that image going in? What does it take up space in your context? How many people, how many people think there may be a special way for the image to get in? Give me a thumbs up if you think there's like a special way for the image to get in. Yeah, okay, you're not falling for it, right? So when you put the image in, it's taking up context. Think about how big images can be. So especially when you saw the super resolution where it does the full image and also the different parts, that is all taking up context. So as you get into models that take in images, that's why you needed to have the Phi 3, which was 128K context, because the image itself is sitting on a big part of the context, takes up a fair amount for it to actually be projected in, plus you have all the text. Great. So some other things to think about. If you want to, we're going to see one example of taking long papers. Oh, actually, Michelle, AI can remember the flow and context coherence of and write long form responses. That's it. That's right. So you can have long running conversations and you can have it generate longer coherent responses, because remember, everything, even in responses, needs to go into that next context for it to actually generate that next token. So it's not like they're separate streams. They're all part of the same thing. Multi-step reasoning, decomposition, curriculum learning, great point. If you ask it to reason through and give you reasons and use chain of thought, that takes up space. But generation of tokens is compute. So you literally have more compute that's available to you as the context gets longer. And by compute, I mean the model considering the problem at hand. So the model has more tokens with which to consider the problem at hand. Tokens take up context, but it also gives better reasoning. These are all fantastic. So one thing which is interesting is coding with long context models. So if you were able to put in a lot of information about the problem you're trying to solve, and you're also able to put in maybe other code that may be relevant, or other code which is in the repo, and against which and with which your code must work, you're going to get much better responses if you're able to include all of that in the context. You know, for example, if you say, oh, I want to have a function that does this particular thing, if all of the previous code and the description of what's supposed to be happening is all in that context, it may say, oh, there's already a function which almost does this. You might just need to rechange to modify it a bit. Or it could say, yes, you can write a function which will do this. In order for this to work with the other functions, it will need to have the following parameters. But sometimes that code base can be really large. And remember, and for those of you who are coders, that can be a really challenging thing when you're trying to add code to something that's huge. This is where long context can really come in handy. Abby, can you talk about how you came up with the example for tuning by proxy from last week?
Yeah, so I'm going to share screen again. And yeah, talk through the process that I went through to create the fine-tuning by proxy notebook. So that was this notebook, which we talked about last week, which covers, yeah, this technique, tuning by proxy, that was in a paper that came out really recently. I believe this year, 2024, April 2024. So super recent paper. And I wanted to build this notebook and interacted with the new ChatGPT 4.0 to create it, and it worked super well and was really easy. So I'm going to try to the best of my ability, recreate this process from scratch. So let's say I have opened a brand new notebook and I want to create this notebook tutorial. And let's go through the steps of what that might look like. So I'm going to start by, I have multiple versions of this chat in case things go awry. But I'm going to start by opening a fresh chat and sticking in this this first prompt, where basically I'm just going to say, I gotta shorten this window a little bit, where basically I'm just going to say, I'm making a Jupyter Notebook tutorial to show tuning by proxy. I want to use a chat fine-tuned version of Llama 7 billion to proxy tune a Llama 13 billion that has not been trained to chat. Can you help me create this notebook, starting with an overview of proxy tuning, then moving on to the code to do this? And I'm letting it know that I want to primarily use Hugging Face in order to do this task. Okay. So here's the start of a Jupyter notebook tutorial for proxy tuning using Hugging Face. So it's going to start by giving me a bunch of steps in order to do this thing. I have sort of asked in my system prompt to lay things out kind of step by step whenever possible, although it is pretty good at naturally doing this. It knows that people prefer things laid out step by step. But I just like to see everything kind of, yeah, set up this way. So we can also always go here and just copy the code. So normally if I'm developing a notebook, I have the notebook open in one tab. I just hit that little copy button and then I go and I run it. I am going to preempt because if we want this to work, there's going to be, we're going to need a good GPU, and we're going to need it to be high RAM. So I'm going to just preempt and open that. So yeah, let me go back to, oh God, I lost my chat. Okay. So we can go through and copy the code and run the cells and just see where things go wrong. That's usually where I start. We can already figure out here so that this is the proper way to load these models from Hugging Face, but you'll see that if I were to run this, I would get an error because it doesn't know where the path to the chat fine-tuned llama is. So it does know that I've asked it to do it from Hugging Face. So this transformers is the Hugging Face package, and we are loading the correct ways to create these models, but this path isn't correct. So I'm not going to run it and get an error. I'm going to just know that that's what's going to happen. But I already have where these models should exist here. So this is the chat fine-tuned llama 7 billion and the base llama 13 billion. I want to point out, if you remember going through this notebook last week, you might already be able to realize that something is wrong here because I've asked to proxy tune and I've asked for these two models, but it has not said, hey, by the way, if this is going to work, you're going to also need the base version of llama 7 billion, the non-chat version. Because we are going to see in a second that it actually doesn't understand what I'm asking it to do quite yet. But I'm going to go ahead and load in the models that it has asked me to load in, which is llama 13 billion and llama 7 billion chat version. And this should run fine, but it will perhaps take, oh no. Okay, well, that's fine. Let's see if it can solve this for us. So I'm on step 2 and I'm getting an error that I don't have access to the models. I'm in a collab notebook. How do I get permission to look at these models? Okay, so it's going to give me lots of stuff, ways to access these models, which we can, of course, say, okay, so I need to like do the notebook login thing. It's giving me lots of information. And if I do the notebook login, I will be able to actually access these models. And let me just grab really quickly my token and stick it in there.
And I'll I'll mention one of the things that is so powerfully enabling about this. Anything that you don't understand, you can ask questions on. And so the whole point is that it's iterative, but but again, with being able to put the entire paper in and then ask questions and actually build up what you need to do, something that simply wasn't possible before, and makes all of this accessible to anybody who has access to these models.
Yeah, so this is going to need to do some work to download. But we can go back to our chat and see, okay, so we've asked it. I explained what the error was. Again, like with long context, that's part of what's so great is that you can not have too much fear of it losing where you were. So I've also just copy and paste an entire error message, and I don't care how long it is, just copy and paste the whole thing in there and it'll figure out what the issue is. Here I'm saying what my issue is because I knew what the error was. But yeah. Okay, so then I'm gonna continue on here to copy this code. And I'm going to see that I need a data set suitable for chat fine tuning. And then I'm also going to look ahead and see that it's setting up training arguments. And I'm going to think to myself that I was pretty sure that proxy tuning was not real fine tuning, so I didn't need to set up a trainer. And that is sort of a great thing, like Jesse was just saying about how you can stick in the paper, because if we go here to GPT-4o and we look at the model description, we can see that GPT-4o currently has, a great context window and a knowledge cutoff date of October 2023, which means that this paper that came out in 2024 isn't baked in already to what it understands, its knowledge base. And it's clear to me by looking at these steps that it's not knowing what I mean when I say proxy tune. It has taken tune to mean just generalized fine tuning, and it's pieced together something, but this is not what I want. So I'm going to redirect it by giving it the paper. So I'm going to say, this looks like actual training. Proxy tuning shouldn't need to train the model. Attached is the proxy tuning paper. Please use the concepts in here to help me write this code. And I'm going to just select the proxy tuning paper, and we're going to stick the entire thing in there. I will say the other thing with long context models is I have the proxy tuning paper open. I can just Control A, Control copy the whole thing and stick it in there also. I find it much cleaner to upload the PDF, but like if you just happen to have it open and you don't have the PDF downloaded, that will also work. Okay, so it's going to take a look at this whole paper. This paper is decently long. And I'm going to give it the whole thing, even with all the appendices that maybe it doesn't need, even with all the references, all 24 pages. They are all going in there because I cannot be bothered to sort through this paper and figure out what is relevant and what is not. And I'm going to let it do that step. Okay, so we can see now that this code is incredibly different after giving it the paper, right? For starters, it has loaded in all three models that we need, right? Remember I pointed out that I could already tell that something was wrong because it didn't ask for Llama 7B, which is a problem because proxy tuning relies on the difference between these two models to figure out how to adjust the logics of this model. The other thing is that this proxy tuning step that we have here is a totally different function than what it called, I'm sorry for all the scrolling, than what it called proxy tuning here, which it just said proxy training and essentially just did a training step. So it didn't understand what I was actually asking for there, but now that I've given it the paper, it has read through the whole paper, it understands the concepts, it understands how to adjust the logits according to what is in the paper, and it's understood that I need a prompt simply, and I just do the proxy tuning depending on one particular prompt, that I don't need I don't need a whole data set that's generated from one of these models to specifically fine tune or anything. So totally different code now that we have vetted the paper. Okay, so we can copy this code and try again and see how it goes. These models are loaded, which is great. I'm going to get rid of this part. And I think that it loaded both tokenizers, which is fine. The tokenizers are the same, so I'm just gonna call what it called in the code tokenizer. I'm gonna pick one because they should be the same thing. And we can see if this will just, oh, and then I have to change these names. So it's doing proxy tuning on base model, expert model, anti-expert model. Up here it calls it. So we can also just ask it to change that if we're really truly feeling lazy, because we can have it rewrite this code as many times as we want. So please rewrite the code you just gave me, but I already loaded the models like this. Now, yeah, I am asking it to just literally rewrite the code. It's not going to change much because the code that it wrote was already correct, but you can see that it's just going to change the naming, particularly up here, of loading the models. Now, I mean, if I'm getting really kind of greedy about not wanting to rewrite the code, I can tell it that actually keep the name how I've already loaded them and change them in the call to the proxy tuning function instead. So, I mean, all of this is unnecessary. I could obviously just go and change the names, but again, just showing how often you can interact with this, have it rewrite the same code over and over again, and it will do the whole thing super quickly. It still knows everything that I'm talking about, and it can change everything that I need it to change. Actually, I don't know if I needed to ask it to do that last thing. It might have already done that for me. That's okay. Okay, so we're gonna see if it actually ends up getting this right, because I had an issue with it before where it was not getting things right. Okay. So it's going to take a second to load in this yet another model that we have had to load in, but hopefully that will still come in okay. Llama 2 is not super, super big. Llama 2 7B is not super, super big. So hopefully we have room for it and this all goes as planned. And then the other thing that I will just show, because it's another kind of great way to do this. So in this instance, I pasted in the paper and it was able to give me really great code based off of the paper. But there also is this really great improve LLMs with proxy tuning blog post that also kind of covers the detail or covers all the details of how to do this and has a lot of code. And this code is really easily copyable. So, but I have already set up my model loading with Hugging Face. So the way that they are doing the model loading in this paper is that, or in this blog post, is that they're assuming that I have like model names somewhere else and that I'm on like multiple GPUs and I'm like mapping them. And so maybe I don't like fully understand how this code is doing its thing, but I do understand how to load stuff with Hugging Face. Another thing that I can do is say like, I found this code online. It seems to work and I want to copy this example, but I want to load the models with Hugging Face instead. Also, I'm on only a single GPU on Google Colab. Please adapt the code to how I've loaded the models on Hugging Face. And then we can go over here and we can just copy code and just dump loads of code again directly into here, taking it straight off of the website. We could take just all of it kind of without any care to exactly if it's applicable or not. And just give it this whole thing of code and say like, rewrite this basically to work with how I'm loading it in. Oh no.
So
Okay.
Abby, what's been your hit rate, success rate when you do that? Because I know you mentioned that last time with it working on the first try. I mean, I know there's so many things that could go wrong, but you just dumped in a bunch of code. I've had